Okay, so we're going to try this out. I have my new toy here. I have my own portable document camera. So I'll see if this works out. So this is an extra set of slides for Chapter 6. This is not for Exam 2, but may be on final exam if you decide to take that. We're going to talk today about model validation and cross-validation. This is actually a really important topic if you're interested in prediction models. So this is really for prediction models. And an optional section you could read here is section 511 of the textbook. I'm actually going to go a little bit beyond what's in 511 of the textbook. And excuse me. And here's an additional online resource that might give you reinforce some of the vocabulary that we're going to talk about here. I'll post this link on Moodle. And we're going to talk about why model validation is important. We'll talk about training and testing data. And we'll do an example of doing model validation techniques on a single data set in SAS, one that you've seen before. And I'll just briefly introduce some cross-validation techniques, mostly k-fold cross-validation techniques, which you may see a bit about moving forward in your career. So I just want to mention that here. So just a reminder, here are the 4 steps that we've already talked about for building a regression model. And today, in particular, we're going to focus on step 4, model validation, which we haven't talked about yet. So we've already talked about aspects of assessing the adequacy. Remember the George Box saying, all models are wrong, but some are useful. And so we looked at assessing the adequacy of our model within our sample data, so whether our model actually fits for our sample data. But then the bigger question is, how well will our model work with new data, or that data that were not used to build the model? And that's what we're talking about when we're talking about model validation. Does our model actually work beyond this sample of data? So model validation is really about making sure that our model is what we call generalizable to a broader population beyond the sample data that we actually use to create the model. We know that our model works for our sample data because those data were used to make the model. Okay? We want to know if the model will use for other data. And that's what we call out-of-sample predictions. We want to know how well our model will work to predict other data. So why is this important? Because we want our model to be useful for predicting other data. Not just the data that were used to create the model, or future data. So we've already talked about overfitting a bit and the importance of variable selection. Just a reminder that overfitting the model, or overfitting the model to the data, is when we use a more complex or flexible model that actually follows the errors or the noise in the data too closely. And that's, well, you often hear the term fitting the noise, or missing the signal and fitting the noise. So let's think about this in the context of data that were used to create the model, and then other data. And let's see if I can adjust this a bit. So we're going to have 2 sets of data that we're going to talk about. We're going to talk about the training data, and these are the observations that we're actually going to use to create the model to estimate the true relationship. And that's what we've been doing so far. And that's really step 2 here: model formulation, variable selection, model reduction, and checking the model assumptions. So this was all done using training data. But then besides training data, our training data are obviously important because we use those to build our model. But in the end, what we really are interested in is how well our model does with previously unseen data, again, out of sample data. Future data points or subjects that were not in your sample or what have you. So the example that we're going to use for these notes are those first year GPA data that we used for class activity 9. So we're going to try to predict first year GPA. So this is first year GPA. First year GPA using high school GPA, SAT scores, etc. But we don't really so much care about the data points that we have in our sample. What we want to do is generalize our predictions to other students who are not actually in our data set. We want to understand these relationships more broadly, not just for those students who are actually in our sample. So the second set of data that we're going to consider are testing data. Or sometimes you'll see the term validation data. These are previously unseen, or more generally data that were not used to create the model, that we also want our model to work well for. So just a reminder, why is overfitting problematic? Because an overfitted model will not give accurate predictions of y for new observations that weren't used to help build the model. So that weren't in the training data set. Remember, the training data set is what we're using to build the model. And we can often get more accurate predictions for y in the testing data with simpler models. So how might we summarize how large the differences are between the predicted and observed values? Well, you've already seen this before. Remember that yi is the observed response and y hat is the predicted value. So recall that our residual is equal to yi minus yi hat. So if we want to know how well our model is working for new data, we could calculate something called the mean squared error, which of course you know what that is. That's the sum I equals 1 to n yi minus yi hat squared divided by n minus k minus 1 degrees of freedom. Remember, k here is the number of slopes. Okay. So that's the mean squared error, but oftentimes in model validation, we don't use the mean square error quite. We use something called the average squared error, or residual will be better, right? Or ASE. And really, it's just a question of what you're dividing by. It's really the same formula, but just dividing by n rather than n minus k minus 1. And it doesn't really matter for our purposes which one you use, because again, we're going to use them as relative measures so we can see which model is doing better. So really, for model validation, either can be used. What we really want is just some measure of error in fitting our model to some new data, which you'll see. And again, we can use either, we can divide by n or we can divide by n minus k minus 1. It doesn't matter. Okay. So just a reminder, if you remember the ANOVA table, let me put it down here. So here's our ANOVA table. Remember that we have model sums of squares, we have error sums of squares, and we have total sums of squares. And the degrees of freedom associated with each of these is k for the number of slopes for the model, n minus 1 for the total sums of squares. So this is n minus 1 minus k because they have to add up the error sums of squares. Okay. So that's where this is where this is coming from. So the mean square error is a measure of how well the predictions from a model, that's the y hat, match the observed data, right? Because the observed data are the y's, the y hats are the predictions. So if MSE is small, when predicted responses are very close to the true responses, we want small MSE. Now the problem is this. We can easily calculate the MSE for our training data. And in fact, remember that the training data are the data that you use to fit the model. And so we actually get that for free from our model. We'll see the training MSE. But for model validation, what we really care about is the MSE for our testing data, or the testing MSE. That is, we want to know how well our model performs with previously unseen data, and is our model generalizable. This again gets to George Box's statement, all models are wrong but some are useful. Evaluating how well our model fits for out-of-sample data is a way of assessing how useful it is. So let's just think about this for a second. Do you think that a model that gives the lowest training MSE will also give the lowest testing MSE? So remember, the training MSE, these are, this means using the data that were used to create the model. Okay. So that's the training MSE, is using the data that were used to create the model, or the testing MSE, which is using new data that had nothing to do with building the model. And the model that gives the lowest training MSE will not necessarily give also the lowest testing MSE, because we know that the training MSE will go down as you add more explanatory variables to the model. So even if we're adding junk to the model, junk that doesn't predict y at all, the MSE will generally go down. So here's just a picture that I borrowed from a, here's the source that it's from in the link down here below. But I think this is a really useful picture. Because what we have over here, we have our training data. Okay. So the circles represent our training data, and we basically fit 3 different models to the training data. The black model is the data, this is the true model. So the black model, is the true model that was used to generate the data. So that's what they say down here. Data were simulated from F, shown in black. Okay. So if you see the black curve on there, that's the model that was used to simulate these points. Okay. So we have a line, and I'm sorry for my, I don't have all my colors on my pens here at home. They're in my office. But we have a line here, which will be simple linear regression. This is just fitting a line to x and y. And you see that the true relationship is curvilinear, so it looks like it might be cubic. Okay, so we might fit a line to this, and that's what that would look like, the yellow line. Okay. We can also fit a very complex model to the line, similar like we did with the airline data, airfare data on the first day of class. We fit this very squiggly line to the model. This is a complex model. And you can see it sort of follows the data very well. But we want to know how well that generalizes to other data points. The blue line that's here, that you can barely see because it follows the black line pretty well, this is a, basically the blue curve is a smoothed out version of the green curve. Okay. You see it actually does a pretty good job of following the black line pretty well. So that's what's going on over here. These are our actual data. These are our training data. They were simulated from the black line, and we fit 3 different models to that. Now what's going on over here in the right side of this graph is on the y-axis here we have the mean squared error, and on the x-axis is just something they're calling model flexibility. And you can think of this as parameters or betas in the model. Okay, so the more flexible model has more betas in the model, and the less flexible model only has, so that the line, so the orange model, I'm going to try to use the same colored pens here to link this up. So these are from the simple linear regression model. Okay. These are from the blue model, the smooth line, and then these are from the complex line. Okay. So let's see what's going on here. So the blue line, or this gray line, I guess, is the training MSE. This is what happens to the training model as you add more terms to the model. Notice that as we make the model more flexible, so it follows the data points, as we make it more flexible, the points are obviously going to get closer and closer to that line because the line is going to more closely follow the points. And so the training MSE goes down. But look what happens. The testing, this is the testing MSE up here. If we fit this to new points, okay, and what will generally happen is the testing MSE will also go down as you add more terms, but eventually the testing MSE will start going up as you start to fit more and more of the noise in your observed data, in your training data. The testing MSE will get bigger. Okay? So we can separate this curve into, or this graph into sort of 3 parts. This part down here we might call underfitting the model. This part up here where the training or the testing curve is separating from the training curve, this is where we're overfitting the model. Okay, so this part down here is underfitting the model, this part up here is overfitting the model. And then this part in the middle, right here, is what we might think of as the sweet spot. That's where we're neither underfitting or overfitting the model, and this is sort of what we're shooting for, is a model where both the training MSE and the testing MSE are reduced a bit. So as I said down here, these are simpler models, and these are more complex models over here, or more parameters in the model. Okay, so hopefully that makes sense. I think this is a pretty cool graph that shows what's going on. And these are just hypothetical data, but keep this in mind because you're going to see something very similar to this in our example. So using the figure above, as the model becomes more complex or flexible, what happens to the training MSE? Training MSE, again, decreases as flexibility increases. And that's generally true in model building, is that as you add more junk to the data, or as you add more junk to the model is going to look better for your sample data, but it's not necessarily going to be better. But now what happens to the testing MSE? So the testing MSE decreases up to a point, but then it increases. And as a model becomes more complex, the training MSE will decrease because you're overfitting or you're fitting the noise in the data. So as the model becomes more complex, the training MSE will decrease because you're fitting the noise in the data, right? But what will happen is eventually the testing MSE will start to increase. And that's when you know you've gone too far. So the relationship between model complexity and training and testing MSE will actually hold regardless of what data set we're using. This is a common pattern. This is a general pattern that we'll see. Overfitting the data, it might seem like you want as complex model as possible, but it can actually lead to worse predictions. It can actually pick up patterns that are just caused by random noise in the data that we would like to avoid. So in practice, we don't know that black model. We don't know the true model. And so we don't have completely separate test data. So how do we estimate the testing MSE so we can figure out what the optimal model complexity is? Is there a way that we can identify that sweet spot where the model is not too simple and not too complex, where we can get the best possible predictions? One way we might do this is through cross-validation or validation.